Hey everybody, today we're going to talk about inverse functions. So our goal is to analyze the relationship between a function and its inverse, algebraically and graphically, and identify the inverse if the inverse is a function. Also, verify two functions are inverses using composition. So you might need to pause this real quick to write all this down. I'm just going to read it, but you will have to pause because you want to make sure you're listening. So an inverse relation maps the output values back to their original input values. So the domain of the inverse relation is the range of the original relation. And the range of the inverse is the domain of the original. So basically, the domain and range are opposite for the inverse. So how are a relation and its inverse related graphically? Well, the graph of an inverse relation is the reflection of the graph of the original relation over the line y equals x. And I'm going to show you what that looks like in just a second. But if you haven't paused yet to write all that down, make sure you do that now before moving on. Okay, so the original relation is given to us in this table. So I'm going to go ahead and graph that first. So -2, 4, -1, 2, 0, 0, 1, -2, and 2, -4. Okay, so that's the set of the original points of the original relation. So if you go back to the definition, it says that the inverse, where the domain, remember the domain are all your x values, is now the range of the inverse. So I need to move my domain down to be the range. Okay, so we're basically putting the x's in the y column, and then we're going to put the y's in the x column, because I'm switching the domain and range, which means I am switching x and y. Okay, so if I graph those, I have 4, -2, 2, -1, 0, 0, -2, 1, and -4, 2. Okay, so now if I look at the graph, and I'm going to draw a dotted line through the line y equals x, right? That starts at 0, 0 and has a slope of 1. That I am reflecting this graph over this line to get to my inverse, okay? And that all of this is lined up in our definitions up here. So it's a reflection over the line y equals x, which I have here in green. Okay, so sometimes when you take the inverse, it's actually not a function. So it can only be a function if for every x there is only one y, and you use the vertical line test to test it out. So the vertical line test means that if you draw a vertical line, you might want to write this down, if you draw a vertical line, it can only touch in one place. Okay, so if I draw a vertical line, and you could draw this line anywhere, you could draw multiple lines, but here's a vertical line going through this one. Since I'm touching my graph twice, it's not a function. Okay, so here I only pass through it once, or maybe you draw it over here, right? No matter where you draw your vertical line, it's only touching your line in one place, so it is a function. Okay? Over here, no matter where I draw that vertical line, I'm only going to pass through the graph one time, right? You could draw it anywhere. So this one is also a function, right? You could draw it over here, right? I'm only touching it in one place, so it will pass the vertical line test, which means it is a function. Okay, so it's not a function when you hit your graph more than one time on any given vertical line. Okay, so let's graph. We're going to find inverses graphically. So you'll need to take out your calculator and type in our function. Alright, so we're going to go to y equals, I need to clear mine, and we're going to type in our function. So 4 times x minus 2 squared. And I'm going to look at my graph real quick to make sure it makes sense. And since that's a quadratic, it does. So I need to get some ordered pairs. So I'm going to go to my table. And I know that this is starting at 2, 0. So I'm going to go to 2, because, right, we did our horizontal shift to the right 2. So I know that the middle here is going to be at 2, 0. I have 3, 4, and 1, 4 on that table. I'm going to get 2 more points to see where I'm at. I'm at 4 and 16 and 0, 16. So I can't really graph those because they're past 10. But we can imagine where they would be. So 2, 0, 1, 4, and 3, 4, and 0, 16 is like way up here. So I know that my parabola looks something like this. Okay? So to find the inverse, right, we need to reflect it over the line y equals x. And if you remember back to the other example, we were at the table and we basically switched all of our x's and y's. Well, we're going to do that here for each point. So that would give me 16, 0, 4, 1, 0, 2, 4, 3, and 16, 4. Right? All I did was swap my x's and y's. So I'm going to graph those. So 4, 1, 0, 2, 4, 3, and then of course 16 is out further. So my parabola looks like that. Okay, so I have my original f of x, mine is in blue, and my inverse, which we write as f inverse with that -1, that's the notation. So f inverse is in red. So is that a function? So I'm just going to quickly sketch it over here. Okay, it looks something like that. So is my inverse a function? Well, let's try the vertical line test. Since it passes through that graph 2 times, it is not a function. No, it fails the vertical line test. Okay? So that's it. Graphing is super easy. Let's do it algebraically. So when we find the inverses algebraically, we need to 1, switch x and y, and 2, solve for y. Alright, just like we did in every example so far, we switched x and y, so I'm going to do that. So then I would have x equals 1/3 y minus 1. And then this is a simple linear equation that we have to know how to isolate y. So I have to add 1. So x plus 1 equals 1/3 y. And then to get rid of that fraction, I need to multiply both sides by 3. And make sure you multiply everything on the left side by 3. So you end up with 3x plus 3 equals y. And that's my inverse. And you could write this as f inverse of x equals 3x plus 3. That would be the proper notation. Okay, so part B, it says f of x equals 3x to the 4th plus 1. Okay, so I know that f of x is really the same as y because it's the mathematical notation that we use. So I'm going to switch those. So I'd have x equals 3y to the 4th plus 1. And then I'm going to solve for y. So I have to subtract 1. So x minus 1 equals 3y to the 4th. And divide both sides by 3. So x minus 1 over 3 equals y to the 4th. Then I have to get rid of my exponent. So I have to raise both sides to the 1/4 power. So that gives me y equals x minus 1 over 3 to the 1/4 power. And that is my final answer. Alright, so that's how you do it algebraically. Again, just switching x and y, and then you're going to have an equation that you've learned how to solve in the past that you have to remember how to solve. Okay, so verify that the following functions are inverses using compositions. Okay, verify means that I already know that they are. Okay, I know that they are, so this will work out. I have to prove using my algebra skills. So I have to show that f of g of x equals x and g of f of x equals x. The good news is that I already know this is going to work out as long as I do my algebra correctly. So remember that. It is true. We just have to prove it using algebra, doing compositions. So f of g of x, so g of x is 1/2 x plus 2 to the third minus 3. And I need to plug that in for x, right? So the 2 and the cube root and the plus 3 and the minus 4 stay the same. So I have to just change x to 1/2 x plus 2 to the third power minus 3. Okay, right? We're just substituting it in for x. Every other number that we have has to stay the same. So then I have to simplify this so it equals x, okay? And you have to follow your order of operations. So I'm going to start under the radical, and I notice negative 3 plus 3 is 0. So then I have 2 times the cube root of 1/2 x plus 2 to the third minus 4. Well, the cube root and the third power are inverses, so those cancel out. So then I'm left with 2 1/2 x plus 2 minus 4. Then I'm going to distribute my 2, see what happens. Well, 2 times 1/2 is just 1. 2 times 2 is 4. Then I still am just bringing down this minus 4. And 4 minus 4 is 0, so I'm left with x. So now I'm halfway done. I showed that f of g of x is equal to x, and then I can move on to g of f of x. So g of f of x equals g of 2 times the cube root of x plus 3 minus 4. Okay, so I need to take g, and everything stays the same. So I have 1/2 times x plus 2 to the third minus 3. Okay, and I need to substitute in my f of x in its place. So 2 times the cube root of x plus 3 minus 4. All right, I'm going to zoom in because I wrote that kind of small. Okay, so the first thing I need to do is go work inside my parentheses, right? Please excuse my dear Aunt Sally. Well, 1/2 times 2 the cube root of 4, I can distribute my 1/2 to this 2 cube root x plus 3 and the 4. So 1/2 times 2 is 1, so I have the cube root of x plus 3 minus 2, because 1/2 times negative 4 is negative 2, plus 2 to the third minus 3. Now negative 2 plus 2 is 0. So I have the cube root of x plus 3 to the third minus 3. The cube root and the third power cancel each other out. So I have x plus 3 minus 3, which is equal to x. Alright, so that was a good example because that was heavily on the algebra and the order of operations. So that's it. Once you show that they're both x, you have verified. But I just want to put this up here that this was f of g of x because I don't want you to, I didn't write that down. Alright, so f of g of x and g of f of x, we have to show that both compositions are equal, that we can simplify them to be x, and then once we do that, we're done. We have verified. Alright, so we'll see you next time.